Thank you very much. So I'll start with the confession that this talk has nothing to do with liquid crystals. So thank you very much for still inviting me. But it has to do with self-assembly, so at least it's hopefully relevant. So it's about self-assembly of colloidal particles at interfaces. So I'll start. Ooh, what happened to that? Oh, yeah. So, so I'll start with an outline of the talk. So this talk is about, as I said, the self-assembly of colloids at a liquid interface. And as I'll show you, colloids are very strongly, if you get the surface chemistry right, they're very strongly absorbed at the liquid interface, so that essentially they're not free to move perpendicular to the interface, but they're free to move laterally to the interface. So essentially we have a two-dimensional colloidal system. We want to study their self-assembly, and that's obviously critically dependent on the interactions between the colloids. So I want to look at that a little bit more detail. I then want to look at the self-assembly of when you have two different types of colloids at the liquid interface. So essentially, that's what I mean by a two-dimensional colloidal alloy, and I'll finish with some conclusions and future work. I'll start with acknowledging my co-workers. So in this talk, I'll present both theoretical work and experimental work. The theory side was done by myself, as well as Adam Law, who was my PhD student and is now a postdoc at the Max Planck Institute for Intelligent Systems in Stuttgart. The experimental side was done by my colleague, Tommy Horozov, a very talented physical chemist, together with summer students Melody Oriel and Dean Smith. Dean is actually a physicist, but in Hull we like to break the boundaries, so he actually did his final year project with Tommy, so that was very, very nice. So colloids at liquid interfaces. So if you have a colloid that's partially wetted by oil and water, what you find is that it will very, very strongly absorb at the liquid interface. This has been known for over 100 years, first sort of pointed out by Pickering, and it is the basis of what we call particle stabilized emulsions, or Pickering emulsions. And that's really, there's been a resurgence of interest in these sort of systems in the last 20 years or so. And the position of the particle at the interface is very much dependent on its wettability, as characterized by the contact angle. So if you have a particle that is hydrophilic, so obviously it will sit more within the water phase, in which case it will have a contact angle that's less than 90 degrees. On the other hand, if you have a hydrophobic particle, it will sit more in the oil phase, and you'll have a contact angle in that case of greater than 90 degrees. Now, you can easily show that for micron-sized particles, which is the sort of size scale that we're interested in this talk, the energy for detaching a colloidal particle from the liquid interface is easily of the order of 1,000,000 kT, okay, for any reasonable contact angle. So essentially, the absorption of these particles at the liquid interface is irreversible. Okay, so they're very, very strongly confined in the interface. So essentially, what we have here is a two-dimensional colloidal system. So I'm interested to look at the self-assembly of such colloids at the interface. So to do that, we need to first of all get a handle on the interaction between particles. And for the experimental system, we will use silica particles at, in this case, octane water interface. The nice thing about silica is that it's very easy to modify the surface chemistry so that you can change the contact angle. More importantly, from our point of view, by changing the contact angle, you can tune very, very strongly the interaction between particles. This is illustrated in this slide here. So here we have 3-micron silica particles, which we've made hydrophobic, so contact angle of 150 degrees. And you see there exists a very, very strong repulsion between the particles, so that they form beautiful sort of hexagonal crystals with long-range order, where the separation between particles is, in this case, 28 microns, so about 10 times the particle radius. However, if you, on the other hand, make the particles hydrophilic, so here, for example, we've tuned or Tommy's tuned the contact angle so that it's 65 degrees, then you drastically reduce the repulsion, and the particles now aggregate. But the repulsion, there is still some residual repulsion, which is why these particles form loose aggregates. Okay, there's a little bit of separation between the two. But the nature of the repulsion in the hydrophilic system is quite different from that in the hydrophobic system, and you can see that by the response to salt concentration in the aqueous phase. So, for example, in this kind of hydrophilic case, if you add a modest amount of salt, say 10 millimolar of sodium chloride, you get a transformation from loose aggregates to close-packed aggregates. So the salt screens the repulsion between the particles. On the other hand, for the hydrophobic colloidal particles, even if you chuck it, say you chuck it about 10 times as much salt concentration, it essentially has no effect on the repulsion between the particles. So clearly, there's quite a difference in the nature of the repulsion between these two systems. And here, I think Tommy is really showing off by preparing particles which are now 63 micron separation, and they're still strong. The repulsion is strong enough to kind of sustain a very nice hexagonal crystal. So we want to get a handle on the origin of these interactions. So I'll start with talking about where the repulsion between the hydrophobic particles comes from. Well, they're primarily electrostatic in nature, but I think you can immediately see that the nature of the electrostatic interactions will be a lot more complicated for colloids at a liquid interface due to this discontinuity in the dielectric constant. Okay, so it's going from oil to water. So you will have contributions, for example, from the diffuse double layer that screens the charge at the particle water interface. And this is asymmetric because, of course, there's no sort of counterions in the oil phase, and that will lead to an effective dipole dipole. So you might have dipole-dipole interactions because of this asymmetric double layer. In addition to that, you will also have some. You might also have some residual charges at the particle oil interface, and although the fraction will be small, the fact is they're not screened, so you don't need a lot to have a big effect. In addition to that, it also has been proposed that you also have contributions to the electrostatic repulsion due to the condensed layer of counterions at the particle water interface. This is what's called the Stern layer. So it's a very, very complex interaction. We've tried to estimate the magnitude of these different contributions, and for our silica systems, we conclude that the dominant contribution comes from the residual charge at the particle oil interface. And the fact is that these are not screened, and therefore they're very, very strong and very, very long range. This is also consistent with the fact that the repulsion for these hydrophobic particles was independent of the salt concentration. Now, although the charges at the particle oil interface are monopoles, because the permittivity of water is so much higher than oil, we can essentially treat it as a conductor. So what you have effectively is you have the charge and also an image charge in the water phase, so that it forms effectively forms a dipole. So the interaction between hydrophobic particles essentially has a dipole form as shown here. This has been measured by many different people, including ourselves. And for our silica particles, the interaction strength is extremely strong, as we've seen. So even at the large separations that I showed, the typical interaction strength is about 2,000 kT. Okay? So, and this is, by the way, sort of orders of magnitude stronger for our silica particles compared to other interfacial colloidal systems that people have studied, for example, polystyrene or other systems, which may explain why we get very, very long range order, as I'll show in a minute. Now, in terms of the attraction between the hydrophilic particles, as we saw, the electrostatic repulsion between hydrophilic particles is significantly weaker. And the fact that by adding salt to the aqueous phase, you go from a sort of loose aggregate structure to close-packed aggregate structure suggests that in this case, the residual charge at the particle oil interface is in fact negligible. And the interaction primarily comes from repulsion due to charge at the particle water interface. Okay, so going back to the salt-free case, we see that for the loose aggregates, the typical separation between particles is of the order of 2 microns. And on these length scales, van der Waals attraction is negligible. So we believe that the origin of the attraction between the particles is primarily due to capillary interactions due to contact line undulation. So although the particles we use are fairly smooth, they're not perfectly smooth, so there's some surface roughness. There may also be some chemical inhomogeneities, so the contact line, in fact, will undulate, and by balancing the sort of electrostatic repulsion and the capillary attraction, we estimate that the amplitude of these fluctuations is about 10 nanometers, which is kind of consistent with the particles being quite smooth. So now that we have a little bit more of a handle about the origin of the interactions between these particles, I want to look at what happens when you have 2 different types of particles at the liquid interface. So I want to look at the self-assembly of binary mixtures of such particles. And we'll make binary mixtures drawn from 4 different types of particles, namely large 3-micron hydrophobic particles, large 3-micron hydrophilic particles, small 1-micron hydrophobic particles, and small 1-micron hydrophilic particles. And we're going to mix them in 3 different ways. So first of all, we're going to look at hydrophobic mixtures consisting of large hydrophobic particles and small hydrophobic particles. And then I'm going to look at 2 hydrophobic hydrophilic mixtures, the first consisting of large hydrophobic particles, large hydrophilic particles, and large hydrophobic particles and small hydrophilic particles. Now, I'll start with the hydrophobic monolayer. So this is a particularly very simple system. It's, the interaction is purely repulsive and dipolar-like. And the structure is basically determined by 3 parameters. Okay? The first is the interaction strength between the large hydrophobic particles. As I said, it's very strong, about 2,000 kT. It also obviously is determined by the dipole moment ratio between the small and large particles, and that goes as the cube of the particle radius, essentially. So the ratio is in fact quite small. So the ratio of dipole moments is about 0.03. Okay, so the dipole moment of the small particles is significantly smaller than that of the large particles. So these 2 parameters are fixed once we fix the chemistry of the system. So what we did then was we looked at how the structure varied depending on the composition of the small particles, okay, the fraction of small particles. So we started with a monolayer of the large particles, and we added a small amount of small particles. And we see that what happens initially is that the small particles essentially fit themselves in the interstitial sites between 3 large particles. As we increase the amount of small particles up to 2 small particles to 1 large particle, we then fully fill all the interstitial sites between the 3 particles. And you form this very nice AB2 sort of alloy crystal structure with a fairly long-range order. If you continue to increase the proportion of small particles, there's no more kind of interstitial sites left between 3 large particles. So what happens is that the small particles then fit into the interstitial sites between 2 large particles now. And you start forming these very, very nice kind of zigzag type of pattern. But what you also see is that as you increase the amount of small particles, you start to get some inhomogeneity and some sort of the degree of disorder. Okay, so the distribution of small particles is not uniform throughout the whole system. So there are some regions that have more higher proportion of small particles than in other regions. And finally, when you go to 5 small particles to 1 large particle, you sort of form these kind of nice honeycomb type structures. So you do have these AB5 unit cells in there, but in addition, as I said, there's more disorder in this sort of system. So you also get some AB6 type structures. But nevertheless, I mean, the structures that are formed are very, very nice. So you get a rich variety of hexagonal superlattices with medium to long range order, I would say. And the kind of pattern that you form is just quite easy, quite a nice, simple motif. Essentially what you have is as you add small particles, they progressively fill the interstitial sites, okay, as you increase the proportion of small particles. And there seems to be minimum distortion of the large particle lattice by small particles. And I think that's purely due to the fact that the dipole moment ratio between small and large particles is so large or so small, depending on which way the ratio is. I mean, there are other sort of co-workers who've studied binary mixtures where the ratio is not as large, say about 0.1, and there you definitely see the small particles will start distorting the lattice of the large particle. So we wanted to see whether we could understand this kind of pattern formation quantitatively. So we did a theory, a sort of lattice sum calculation. This is basically an energy minimization scheme. So you're basically calculating the structure at 0 temperature. And that's reasonable because, as I said, the interaction energy is very, very strong in these systems. So one might expect that to a first approximation, you can neglect entropy. So what you do is you calculate the energy per unit cell as a function of various lattice parameters, including the ratio of lattice constants, the angle between the lattice vectors, and also the position of the small particles within your unit cell, and you minimize. Okay? So here's sort of some of the results that we get sort of for the interaction strength and dipole moment ratios in our system, and just varying the composition of small particles. So for 2 to 1, we get this nice AB2 structures. So obviously there's no disorder in this because it's an energy minimization scheme. For 3 to 1, you get the particles lining up along the long diagonal, and 4 to 1, you get sort of zigzags. 5 to 1, you get, well, almost the AB5, but not quite. So it's not, the calculation is not perfect, but it's reasonably close. And then finally, 6 to 1, you get these AB6 type structures. So at least at a local level, the lattice sum method is reproducing the local structure of what we observe. And indeed, we've also done some finite temperature Monte Carlo simulations, and those also help us to understand to some extent why it is that as you go to higher proportion of small particles, you start getting more disorder. Okay, so that was the hydrophobic mixtures, and I want to just briefly talk about hydrophilic mixtures. Okay, I will better rush through this. Sorry about that. So here, so this is just to remind you. So we've got sort of large hydrophobic particles and large hydrophilic particles. You form for 2 to 1, you form these linear AB2 type clusters, and 6 to 1, you form these trigonal AB6 type clusters. Whereas for the small particles, you start having small particles coating the large particles. So again, a rich variety of superlattice clusters, and you notice that the clusters themselves are arranged on a hexagonal lattice, and the structure of the mixed cluster is basically controlled by composition and packing geometry. And the one striking thing I want to point out here is due to the hydrophobic particles, there exists a selective attraction between the hydrophobic and hydrophilic particles, because you notice that when you mix the two, you never ever form clusters purely consisting of hydrophilic particles. They're always mixed clusters. So clearly, there's some, induced by the hydrophobic particles, there's some selective attraction between hydrophilic and hydrophobic particles. Also, there's a kind of repulsion between hydrophilic particles within the cluster. And you can see that most clearly in these AB2 structures, because they form these linear AB2 structures rather than a compact AB2 structure. So our theory on this is that these are due to induced dipole interaction. So the hydrophobic particles have a strong effective dipole, which induces a dipole which is of opposite sign, so that it's attractive between the hydrophobic and hydrophilic, and repulsive between the hydrophilic particles. Once again, we've incorporated those induced dipole interactions into a lattice sum calculation, and we're able to reproduce a lot of the cluster structures, at least on a local level, that we see in the experiment. So, conclusions. So we've studied mixed colloidal particles of hydrophobic and hydrophilic particles. We see that they exhibit a very rich variety of superlattice structures. And more to the point, that the structures can be very, very nicely controlled by tuning particle interactions through tuning surface chemistry, composition, and packing geometry. We have excellent agreement, at least at a local level, with theory, which shows that we have a reasonably good understanding of underlying forces driving these self-assembly things. Essentially, the structure seems to be stabilized either by long-range electrostatic repulsion or short-range induced dipole interaction. well, I think I've run out of time, so I will leave that, just flash that up. Thank you very much.
You said it, but I missed it. What is the interaction that you assume between the spheres? Is it dipolar or is it Amaker type?
No, it's not Hamaker because the separations are microns, you know, so it's not van der Waals at all. It is, so we believe for our silicas, it's a controversial topic. What's clear is that there is strong repulsion, as I've shown. Now, where it comes from, there's still a matter of debate. Our opinion is that it primarily comes from residual charges at the particle-oil interface. Now, those are monopoles, but because the water phase has a high permittivity, it essentially acts like a conductor. So basically, the residual charges have an image charge in the water phase. So the charge and image charge form an effective dipole. So the interaction, in fact, is dipolar, dipole.
But then you assume that it works like a point dipole. I mean, the interaction is r to the minus 3.
Yeah, so in all our theories, we assume it goes as 1 over r to the cubed.
R to the minus 3, while if it was Amaker, it would be 1 to the, more or less, distance to the minus 1 for this large sphere, so it would be very long range. I wonder if you...
No, the long range, the hydro... No, for the
minus 6 for point, but if you have Amaker, I mean, very large sphere, it goes as 1 over h, where h is the phasing distance.
Okay. No, so we assume a 1 over r2 cubed. That seems to give us good agreement with the structures. Now, the hydrophobic, hydrophilic, because that's kind of quite short range, there we do have, as I said, it's a dipole-induced dipole. So in fact, that goes as 1 over r to the 6th. And we do kind of account for some local effects, like the things are not quite in the same plane, and that sort of stuff. So, yeah.
Okay, I think we have to cut it here because I did promise we'd finish on time. I'd like to say thank you to all our speakers, first of all.